Today we're going to take calculus and make it 3D. So we're going to talk about the disc and washer method, so come on and join me. Today I'm going to teach you all about the disc and washer method. The very first thing you must do in all of these problems is sketch it on your paper. This is critical to you being able to understand what is going on. Today I'm going to show you some 3D versions as well to help you visualize what is happening. But step number one is get all this down. Make sure you have the function graphed. So you'll see I have my square root of x graphed here and my x equals 4 line. We're going to rotate this thing around the x-axis. It's going to spin over this line right here. And it's just going to keep spinning. So what does that look like? I'm going to show you a 3D version right now so you can see what this function, bound by y equals 0 and x equals 4, will look like if we take it and we spin it. So now we have a visual of our graph. Right here in the black, you see our square root of x bounded at x equals 4. And I want to spin this thing around the x-axis. So let's take a look at what that creates. I'm going to spin it around the x-axis, and hopefully you see this new shape that it creates. And you can see that this is a circle shape that has been created. Notice there's no hole in the center. So we call these things discs. They're kind of like a frisbee, right? There's no hole in the center. This is a disc. And this is called the disc method that we're going to use. And notice the shape you have here is a circle. So the question is, how do we use this circle? Well, notice right here I have a lot of these rectangles, right? We've been using rectangles a lot in integration. And notice the more rectangles that I make, the closer and closer to the curve it becomes. And that's exactly what we want. And that's why we use integration. I'm going to go back and so you can see just the rectangles as I rotate this. So we're going to take these rectangles, we're going to rotate them around the x-axis. If you look at this picture right here, you'll see that I have a nice outline of those rectangles. So if you slide those rectangles around, it makes that circle shape. And then you can see that those rings were created from the rectangles. Well, what we want to do is how do we use that? So what you'll notice as I slide this is that the radius is what we are going to use for that circle shape. Now that you've got to see what that looks like in a 3D version, you have to try to show that on your paper somehow. And I'm going to teach you how real quick. So what you want to do is you're going to draw the shadow of what you saw. So if this is the function, the shadow is going to be like down here, right? And this is the area, the circles that were created between the function and the shadow as it spun around. What shape is that? Obviously you saw that it was a circle. So we can find the area of that circle, but a circle is a 2D shape. When we spun that thing, it was 3D. So we need to add a third dimension. That third dimension is the tiny changes in the x value which stacked those circles. Because the circles were stacked like this, there's tiny circles all along here, along that x-axis. That's why it's a dx problem. So how do we set up what we're going to do? Obviously, we're going to add up, right? Integration is how we add up in calculus. The area of a circle and tiny changes in our x values. This is it. It's going to be a circle equation, which is your 2D shape. The dx adds that third dimension, which makes this a 3D shape as it is spinning around the x-axis. So here we go. The integral, pi. What is the radius of this circle? Well, the radius from here all the way up. And this one from here all the way up. So what is the length of this radius? It's your function minus whatever line it's spinning around, which in our case happens to be 0. So the height of this radius is our function, which is the square root of x. Now what are our bounds? We said it's going to start at 0 and it's going to go to 4. To solve this problem, you're just going to stick it in your calculator. So in your y1 in your graphing calculator, pi, square root of x squared is just x, and then you're going to evaluate from 0 to 4. So once you put this in your calculator, you will get 25.133 for your rounding, for your answer. So this answer we got reflects the volume of that function being spun around the x-axis. Notice there's no holes in the center. That's why this is called the disk method. Let me show you what it looks like if there's a hole in the center. So now I'm going to show you about the washer method. We're going to take a similar problem, but I'm just going to change where we spin the function around. So in this problem, we're still going against the x-axis. We're bounded by x equals 4. We're bounded by the y-axis and 0. This is the area that we are going to spin. But this time, we're spinning that guy around y equals -2. So if you can picture in your mind what that looks like, we have to spin this over this way. So let's take a look at what that means for a 3D picture. Okay, right here we have it visually. We have our square root of x graph. We have it bound by x equals 4, and we want it to revolve around y equals -2. Now, as I revolve this area right in here, I want you to see what happens with the shape. So I'm going to revolve it, and as I revolve it, you should see that there is a hole in the center between y equals 0 and y equals -2. So that same space has to be reflected below. And therefore, we have what is called a washer. Just like if you look at tools, it is the shape of a washer. Another example of that same problem is right here. So along the top here, we have square root of x and y equals 0 at the bottom. And here you have the washer that was created when we revolve around this y equals -2 line. Notice now I will show you all of the disks if we did it from 0, there's 0, all the way to an x is 4. So it's making all of these washers in between, and this is what we will use. We have this bigger circle here on the outside, and we will subtract this inner circle away to get the volume of the shaded area. Now that you've seen that 3D picture, let's try to put this on our paper, because this is going to be critical for you as you're doing this at home on your paper to understand how this is reflected and what it looks like. So the first thing is there's this space right here that we have to show down here. So right here, that's the same space that we have. And then we have our square root of x function like down here. So here is the space that I like to call the shadow. This is what I call the shadow of what is being flipped around that axis of rotation. So how do we set this up? Well, you've got a big circle in here like so, and then you have a small circle in here like so. This is why we call it a washer, because there's this hole, this space in the center. Or you can call it a donut, whatever you want. In calculus, they call it the washer method. Most people like to call it a donut. But this is what you have to deal with when you're setting up your equation. So again, we're still adding up a bunch of circles along our x-axis. So dx is still going to be the boss because the circles are being stacked along the x-axis. Now we have two circles. So we're going to have the area of the big circle minus the area of the small circle, because we have to take out that centerpiece that's not being used. And we knew that this is a dx problem. So washer method is going to be a big circle minus a small circle. All right, so let's set up. We know that this problem is going from 0 to 4, again, because that was given to us in our problem. pi, the big radius. Let's talk about this big radius. So this big radius starts at the function and it's going all the way down to y minus 2. So again, kind of like area between curves, top minus bottom. The top function is the square root of x minus a negative 2 squared, because this is my big radius. Minus, that's this minus piece right here. Now let's do our second radius. Pi, our small radius goes from x equals 0 to y is negative 2. So it's really 0 minus negative 2 squared. Or you can just understand that that distance is 2 and put a 2 in there. And then this is a dx problem. So I brought these images over from the 3D imaging so you can see what one of the washers looks like and then the stack of washers. So let's clean up our equation. The integral from 0 to 4 of pi square root of x plus 2 squared minus 4 pi, right, once you simplify your math there, dx. Then you go ahead and you put this into your calculator and make sure you integrate from 0 to 4. You should get 92.153 for a final answer. And that is how you do a washer or a donut. Okay, let's do a slightly different problem. Now we solve the square root of x, but this time the area we want is going to be bounded by y equals 2, the square root of x, and x equals 0. So this is the space we're rotating over the x-axis. We're going to spin it around the x-axis. So let's take a look at what that is going to do in a 3D image so we can see the volume it creates. When you go over here to our visual, we have our line here at y equals 2 in blue, and then our square root of x in green. So it's just this small space in here that I'm looking to revolve. And let's see what happens when I revolve that small piece. When you revolve that all the way around, it's just a small piece, and the shadow is down here in that small piece, making the circle. Again, we have a washer with a hole in the center. So when we come over to this example, again, these dots are bounding in the area between y equals 2 and the square root of x. So here's the area that we're reflecting, and notice they show the shadow area down over here. Let's take a look at one of those washers and see what that looks like. So I'm going to move the washer along this area. Notice how it's changing because that square root of x curve is on the bottom. It gets really skinny right here at the end, but over here it is thicker. I'll leave it right there in the center for us to kind of get a good example. And let's show in some other discs here. As we have the other discs that are filled in, you can see how it changes along this area that we're looking to find the volume of that shaded area. Now that you've seen the 3D image, the very important thing you have to do is remember to try to draw on your paper. So let's do that. So I'm going to take this and I'm going to create this down here at y equals negative 2. I'm going to create my square root of x, something like that. And my shadow space is actually this piece down here. So this is where my shadow piece goes. So that means my circles are in here and then in here. So again, for a washer or a donut method, you need to subtract a big circle minus a small circle. So we have the integral pi of my big circle, the area of my big circle, minus my small circle, and then these circles are being stacked against your x-axis, so this is going to be a dx problem. So that means your bounds and everything right needs to be in terms of x. So we're going to integrate from 0 to 4 because it starts when x is 0, and right here where they intersect, our x value is 4. Pi, now our big radius. What is our big radius? Well, if you go from here all the way down, it starts at 2 and it goes down to 0. So our big radius is 2 this time. Minus pi, what's our small radius? Well, our small radius, do a different color. Our small radius starts at the function and goes down to 0. So our small radius is the square root of x squared. dx. So again, you can clean up that equation, stick it into your y1 in your calculator. So the answer to this, when you round, will be 25.133. We're going to try one more example, and this one's a little different. Notice it wants us to spin it around the y-axis. So again, make sure you have this drawn. Notice we're being bounded by y equals x, and then up here at y equals 4, and the x-axis. So this is the area that they want us to spin. This time they want us to spin it around the y-axis. So think about that for a minute. Do you know what that shadow will look like without having to go to the 3D image yet? Try it, because this is what you're going to need to be able to do, is to spin these in your mind and see what this looks like. So if we want to draw the shadow of this, our line's going to go this way. Our shadow is actually going to be this side over here. Which means our circles are going this way. So notice there's no hole in the center, which means we have a disk, which is just one circle. But what happened? Now our circles are stacked on the y-axis, because that's where they had us spin it around. So this is going to be a dy problem, which means all of your variables and your bounds have to be in terms of y for this problem. So let's go ahead and take a quick second to see what this looks like in a 3D image, so you can see the circles stacked on top and the volume that is created. Okay, so on the screen you can see our x equals y and our y equals 4. And what we want to do this time is we're going to spin it around the y-axis. So what happens when I spin it around the y-axis? It goes all the way around. Now if you look at it like this, it just looks like it's a triangle. But you have to remember, this is a 3D image. All we're seeing is a 2D. So if I tilt this forward, you can see the top of this created a circle. And because there's no hole in the center, this is known as a disc, right? Or I like to call them frisbees. And so that's again what we will use for this problem, is we will use the disc method to solve this. And this circle will be what we use, and the radius will be from the edge of our function to our x equals 0 line. From the 3D image, you saw that it's still circular on top, but it's volume, so we had to have that third dimension, which is going to be dy in this problem. So we're going to have the integral, and we're going to do a circle, but this time it's going to be in terms of y. And what are our y bounds? In this problem, they are 0 to 4. So now, how do we find our radius? Well, your radius is right here. This is where your radius is going to be from. So how do we find that? Right minus left. So in this function, it's y equals x minus 0, which is a really nice example. But you just have to remember that for your radius in dy problems, you're going to want to do the function on the right minus the function on the left. And that will help you set up your radius. So for this problem, we have the bounds from 0 to 4. Pi, our radius, which is nice, our function is nice, we have to write it in terms of y squared, because radius squared, dy. So this would be the function that you have for your answer. In your calculator, you can still put in y1 equals pi x squared. Make sure you evaluate from 0 to 4, though, for your bounds. And you will get an answer of 25.133. Hopefully this helps simplify the disc and washer method for you. Really, it's just the area of a circle. Make sure you're just paying attention. Draw your function, draw the shadow, draw the line for your radius. If it's a dx problem, it's going to be top minus bottom to find that radius. If it's a dy, it's going to be right minus left. Make sure you know if it's a dx or a dy, and make sure your bounds go according to that. Be sure to share this with another calculus friend, and make sure you subscribe.